this video. This video is on Espresso Logic Minimizer Algorithm. This video is presented by students of MTech AI at IIT Patna. We are Prateek, myself, Ankit Pandey, and Saumyadweepta Paul. And we have made this video under the instructions provided by Dr. Arijit Mondal, Assistant Professor, Department of Computer Science and Engineering, IIT Patna. And this is Espresso Logic Minimizer. It is a minimizer heuristic technique, and it reduces the number of terms. That means it eliminates all the redundant terms from the uh, logic and merge the implicates. So here's more about it. Espresso Logic Minimizer is a simulated annealing method, or you can say it is based on one. Here in the simulated annealing method, we go towards finding the most minimum number of terms. So it can be a local minimum or a global minimum. So based on this technique, we tend to go towards global, but it may never be the exact answer. It will always be near to it. And simulated annealing method is a kind of local search technique. It is used to determine the solutions for NP-complete or NP-hard problems, which have a large amount of data, which will be hard to traverse over all the terms, and it will be computationally very complex. And there are three steps to it. The first one is expand. So here you can see in the Boolean logic, there are three number of terms which will denote a cube. In this three-dimensional cube, each towards each axis there will be expansion, which will cover the min terms. Here min terms are circled. So here one is representative of exactly that. And here we will also find the prime implicants, which will have no adjacency or no overlap over other ones. Now, in irredundant steps, we will do opposite of what we did in expand. We will find the irrelevant or redundant number of covering, or you may say circles. Like here, you can see in the image that this one term is also covered by another overlap. This is redundant, so we our motive is to reduce that to reach the optimal setting, and our only goal is to keep essential primary implicate and also remove extra terms. Now, in the third step, we will do exactly what we discussed in a redundant step. So we will remove all the unnecessary literals. The one here you can see, and the which in 0, 1, 1, 1, and 1, 0, you can see three ones are there, and they are covered by three different individual circles. And here you can see both have been removed. Both are done this way, and the vertical one has been separately circled. This is giving us the optimal setting. So it will always make us go towards this kind of setting, which will be optimal, but it is not always uh, mandated. So, but most of the times, almost all the times, it is doable. So now we will move towards literature survey, which will be covered by Mr. Ankit Pandey.
Hi, I am Ankit Pandey and I am done literature review on Espresso algorithm. The first one is the Quinn-McCluskey method versus heuristic logic minimization technique. In this method, Quick-McCluskey minimize Boolean function using a tabular method. And you know about tabular method? The tabular method minimization approach that groups min term based on the number of oneness in binary representation that is given in this figure. So group minterm by oneness binary representation combine adjacent group iteratively. So more efficient than K-map for large variable, but there is one problem, that is NP complete problem. In this problem, it guarantee an optimal solution but suffer from exponential time complexity. So next heuristic method like Espresso preferred for scalability. And you know why heuristic method like Espresso? So, to overcome the limitation of QMC heuristic-based method such as Espresso were introduced. This method does not guarantee an exact minimum, but near optimal solution efficiently. So, faster execution, avoid executive searches, and use intelligence heuristic, memory efficient, and research the trend. Recent research focus on parallelization and modification performance. So next literature review is Espresso algorithm introduced in logic minimization algorithm for VLSI synthesis in 1984. So in this literature review, heuristic method for Boolean logic minimization and key step is expand, irradiant cover and reduce. So first you know about expand. Expand merge adjacent term for broader coverage. In expand, so let's assume there is a K-map graph, and in expand we merge adjacent boolean for expand the logic minimization. So second one is irradiant cover. In irradiant cover, remove unnecessary term that do not contribute to the function. So those function do not contribute in function, so we can remove. And next one is reduce. Reduce is iteratively refined to improve local optimality. In this, the algorithm shrink expression further by eliminating redundant literals. So next one is set-based logic minimization combines Espresso 2 with set solvers. So in this literature review, improve runtime by 5 into 2x over Espresso 2, efficient for large problem that is 100 plus variables. So Espresso gained widespread use. Researchers sought a way to improve its accuracy while maintaining its efficiency. This led to set-based expressor 2. So what is set-based minimization? In set-based minimization, instead of relying purely on heuristic transformation, set solver analyze logical equivalence and constraint to improve minimization accuracy. Set-based technique speed up certain computational step in Espresso while ensuring more optimal solution. So optimize key of rater, reduce irritant that is previous cover, and achieve near optimal solution faster than traditional method, outperform boom and heuristic only approaches. So next one is Espresso GPU is a parallelized version of Espresso 2 for a two-level logical minimization. In this minimization, leverage GPU computing CODA for massive speedup and achieve an average 97 into a speedup. So first is why parallel computing? Parallel computing is because traditional Espresso perform computation one step at a time, and Espresso GPU distribute tasks across a thousand of GPU cores, enabling parallel processing. So let's cover key features of Espresso GPU. That is 97x speedup over serial Espresso 2, highly scalable for large scalable Boolean function application in performance computing, and ideal for application like neural network inference and large circuit optimization. So next one is application of Espresso algorithm. Now it's time to cover application of Espresso algorithm. In digital circuit design, Boolean function define logic gates and circuits. So first, it's helps to complement calculation, identify simplification opportunity, expand merge meantime for broader coverage, remove unnecessary literal cover, keeps only essential terms, and stop when no further improvement can be made. So fault diagnosis and digital circuit design and embedded system, machine learning and AI, this all are application, and other implication is minimize Boolean expression, hardcore cost power consumption, and process speeding. And next one is comparison between three of comparison between four of literature review that I covered recently. So approach is Quinn McCluskey approach is exhaustive search, and this efficiency is low, slow for large input, and scalability is poor, that is exponential growth, and optimally exact. Espresso is approach heuristic and efficiency is high, order faster, and scalability is excellent and a large system and optimality is near optimal. So SAT Espresso is based on SAT based heuristic approach and very high 2x faster and scalability excellent and optimality near optimal. And Espresso GPU parallelize X heuristic extremely high 97x faster, that is efficiency, and accessibility is exceptional and optimal is near optimal. So Espresso, SAT Espresso and Espresso GPU all are near optimal and Queen McCluskey is exact optimal. So that's all we cover, and next is Espresso algorithm that is covered my colleague Saumyadweepta Paul.
Hi guys, Saumyadweepta here. So I will be talking about the Espresso algorithm. The Espresso algorithm is a Boolean minimization function algorithm. The Espresso algorithm iteratively refines a given Boolean X function by simplifying it step by step. It first computes the complement of the function to identify the don't care conditions, making the simplification a bit easier than the other algorithms. The process continues in a loop of expansion, reduction, and irredundant cover until no further minimization is possible. This is basically the Espresso algorithm method, ensures a highly optimized and an efficient Boolean expression, reducing logic gate usage in the digital circuits. A-star algorithm for the Boolean function minimization. An A-star algorithm is basically an alternative pathfinding algorithm. It is an informed search method which is used to find the shortest path in a weighted graph. It combines the actual cost from the starting point to the current node, which is basically the GN. The HN is the heuristic function, which is the estimated cost from the current node to the goal heuristic. The better the heuristic function we design, the better the optimal result we get. It ensures the optimal and efficient pathfinding when a proper heuristic is used. The A-star algorithm structure for the Boolean function minimization. A-star selects the node with the lowest cost. We basically get the cost by adding the GN and the heuristic function value from an open list and expands it by exploring its neighbors. Each time a neighbor is visited, the algorithm updates the cost and the path, ensuring the best possible route is chosen. This process continues until the goal node is reached, at which the point optimal path is reconstructed. The efficiency of A-star depends heavily on the choice of the heuristic function. A poor heuristic can lead to a slow or inefficient performance. The A-star for the Boolean function minimization, which is basically we define the state space and the initial states and all, and the problem of the state explosion in Boolean function minimization. When A-star is used for Boolean function minimization, it often explores too many redundant paths. Since Boolean minimization involves a large number of variables and combinations, A-star suffers from the state space explosion, meaning it requires too much memory and processing time. This makes the A-star inefficient compared to the heuristic-based approaches like Espresso, which are specifically designed for the logic function minimization. For large-scale circuits, Espresso is preferred because it avoids exhaustive search and directly finds the optimized results. So this is basically the continuation of the previous slide, and in which we basically say that A star struggles with the Boolean minimization because it lacks a well-defined heuristic function for this type of problem. The algorithm expands many unnecessary nodes, leading to excessive computation. In contrast, Espresso efficiently identifies prime implicants without exploring all possible solutions. This makes Espresso a more practical choice for minimizing the logic functions in circuit design and digital computing. The Espresso algorithm basically finds the prime implicant without the exhaustive search. That's why we should not use the A star algorithm for the Boolean function minimization. So A star, we can conclude that the A star leads to combinatorial explosion in Boolean minimization, while specialized heuristic like Espresso yields result efficiently. So we can conclude that we should not use algorithms like A star, DFBB, because they work similarly, because and the heuristic function is not very optimized for such purposes. So we should basically use the Espresso algorithm for the Boolean function minimization, and it is specific, and the Espresso is specifically designed for that purpose only. So this is the conclusion we derive from all the project work we have done, that Espressos iteratively refines Boolean expression until a near optimal solution is reached. It is highly effective in minimizing circuits with thousands of logic gates and making it ideal for VLSI design and large-scale digital systems. Unlike exact methods, Espresso find high-quality solution within minute, even for complex Boolean functions with thousands of variables. The efficiency makes it one of the most widely used algorithms in hardware synthesis and AI-driven logic simplifications. These were references which we have taken help from. These are basically the 4 references which we have taken help from, and so this is the end of our project. Hope you all got a clear understanding of the Espresso algorithm. We all tried to give a clear and detailed explanation of it, and thank you, and have a nice day ahead.